Chapter 2, Process and Threads. We will spend lots of time on this. So for an operating system, the most central concept, most central idea is the idea of process. Most central concept in an operating system is the process. Process is an abstraction of a running program. Okay, so we talk about abstraction a lot in programming languages and in programming languages or in learning object-oriented programming. Abstraction is central to many this one. It doesn't work. Okay, I won't write anything. So abstraction is said that process an abstraction of a running program. That means we have a model of a process, and we use a software model to represent the process. If we change parameters of that model, then we are changing the parameters of the running program. If we wanted to know anything about that running program, then we go to that abstraction and ask questions. Okay, when did you start running? Who created you? And what kind of files you open, that kind of stuff. So again, like we did class abstraction for some kind of a code, we are using this abstraction model to represent the running program. Processes are one of the oldest and most important abstraction of the operating system. They started modeling the processes at the beginning, and they kept enhancing these models over the years to arrive at what we have today. Okay, processes, they support the ability to have concurrent operation when there is only one single CPU. Even if you have a single CPU, due to this abstraction model, each process might think that it has its own CPU, which is the fundamental tool for the multi-programming or time sharing of the CPU. Using this process abstraction, we turn a single CPU into multiple virtual CPUs. The virtual CPUs, these virtual CPUs are not real CPUs; they are virtual. Okay. Using these virtual CPUs, we might run several processes at the same time, or at least it seems that way for the user, without adding new CPUs as hardware to our system. Without the process abstraction, modern computing could not exist. So the processes are that important. Let's say I have three processes, 1, 2, 3. Here I have three processes. 1, 2, and 3, and they are sharing the same CPU. Since there is only one CPU, only one process can run at the same time. So we do time sharing. At this time slot, time slot number one, I am running process number one. Time slot number two, I am not running any processes. Why do you think this is the case? Why I am not running any? Okay, let's go back to this question later. At number three, I am running process number two, then number one, then number three. It goes like that way. But here and there, I am not running any process. Why? That is wasting my CPU time, right?
Yes.
Why don't I run any process here and there?
Maybe they are doing input-output operations.
Maybe all of them here, okay? Process 1, process 2, and process 3. They ask for an input-output operation. They want you to read some data from the disk or from the keyboard. And disk or the keyboard is not ready to provide that data. So none of them can run at that time, okay? So we have to wait. Sometimes processes have to wait because the data is not ready, okay? They are blocked. That's why we have this multi-processing idea, right? If one of the processes cannot continue, maybe we can let the others run. If none of them can continue, then we are not going to run any of them, okay? We are not going to run any of them. In fact, remember I showed the processes that are running on this computer. So the CPU usage is here. As you see, all these processes, like 50, 60 of them, they don't do anything, they don't run, okay? They just wait. Why are they waiting? Because they are waiting something to happen. This one, Windows logon application. This process only works when there is a logging in process happening, okay? So since I am logged in already, that process is going to sit until I log out and when I try to log in. When I try to log in, that process is going to run again. It will sit somewhere. TeamViewer server here, I have installed it, but it is not running because I am not using TeamViewer. It sits somewhere and the memory it is blocked and it is not running. But some programs, like these programs at the top, Task Manager itself, this program, okay, and Window Manager that manages all the windows, the system itself, the kernel, the scheduler, and the interrupt routines, they are all working, okay, they are doing some stuff. So this operating system has 3 processes, my operating system has 60, and sometimes none of them work, sometimes some CPU cycles are, remember this one? In my computer now, I am using only the 10% of my CPU time, or 1% of my CPU time. 99% of now it is 0, right? Nobody is using anything. So So I am at this phase. Nobody is using anything. If I do some stuff like, if I do this, because I am now using CPU time, the task manager or the Windows C, so the desktop manager and everything starts working. But if I stop doing anything, then it's going to go to 0% again. So most of the time my computer doesn't do anything, sits idle. So this is not a rare case, okay? Especially for this kind of computers. This is not a rare case. For this computer, it is okay to have this kind of idle CPU time because this is a very cheap system, okay? It's a personal computer. But if I have large number of idle slots for a $1 million server, that means that I am wasting money because I paid $1 million and I am not using my computer. Most of the time, my CPU cycles are wasted. That's a bad thing. But for these kind of computers or these kind of computers, if I don't have anything to do, then what can I do? I have to sit and there because the computer is not that. My computer is not that expensive. It is the same thing as having a car sitting in there. Nobody's using it. I mean, is it a waste of time? No, because I bought that car just to come to work and go back home, right? But if I bought an airplane, okay, if I paid $5 million, $10 million for an airplane, and I am sitting that airplane in the airport all the time, then that means that I am wasting my money, because that airplane is going to be outdated in 15 years, and I'm gonna lose that money, all of that money in 10 years, 15 years, $10 million. That's a bad thing. That was the main idea of having this multiprogramming. Computers don't really run multiple programs at the same time, okay? They don't really run multiple programs at the same time. It just appears that way. I can only run one process at the same time, okay? But if I do this switching very, very quickly, let's say from this time to this time, only 1 microsecond or 1 millisecond passes, a human observer would think that 3 processes are running at the same time, like I am doing with this computer. Only one process, if I have only single CPU, is running at the same time. Each process runs to completion, but intermixed with other processes. Each one runs to completion. Each one does all of the jobs of whatever it is assigned to, but they intermix with each other. So that's the idea of multiprogramming. And when I look at these are directly from the textbook, these figures and the text actually, copy-pasted. If I have 4 programs running, multiprogramming, in my computer, I need to switch from process A to process B to C, then process C to D. So this is called process switch from one process to another one. If I do this fast enough, then my user thinks that my computer is running 4 different processes at the same time. Okay, conceptually, processes if you look at from the user's side, user thinks that there are 4 processes running at the same time. But if you look from the process's perspective, the process thinks that it has the whole CPU to itself, it has the whole memory to itself, it has the whole computer to itself. The process thinks that it owns the whole operating system and the hardware, right? From the user's perspective, users think that there are 4 processes or 80 processes running at the same time. In reality, of course, the real CPU switches back and forth from process to process. But when you are writing programs, you don't care about the other processes, other things. When you write a C program, you write your C program and you run it, and you think that only your process is running in the program, in the computer. You ignore the rest of it. It's a very complicated operating system. 80 processes are running, but you don't care about them. You only care about the program that you are developing, or you care about the useful program that you run. Okay. Okay. What else? So, if you conceptual model for independent and sequential processes, A thinks that it is running by itself on the computer, and the same thing for the B and C and D. Okay. So, in this chapter, when we talk about the processes, we will not talk about multiple CPUs, okay? We will always assume that there is only one CPU. And that CPU has to be shared by many processes that the operating system has to run, okay? Nowadays, this assumption is not true anymore, because most CPU producers they don't sell any single core CPU anymore. They sell multiple core CPUs. They have at least 2, 4 or more CPUs inside a single CPU, because they can do it. It costs the same as the single core CPU. So why not have 88 core CPUs? We talked about this, and in some cases with the GPUs, you can put hundreds, sometimes thousands of GPUs on the same chip with the same price. So why don't we do it that way? So this assumption is not valid in the real world, but this assumption is very good in terms of understanding the task of the process. What's the process? How do we do multi-programming with a single CPU? That's why our assumption is okay in terms of understanding, for the sake of understanding the process model. Okay, so this is another way of looking at these four processes. Again, this is time, CPU time. CPU spends its time with process A here, then B, then C, then D, then it goes that way. It doesn't have to follow the same. It doesn't have to follow the same same sequence all the time. But as a representation, the book gives this example. Okay. By the way, these areas, these durations, they don't have to be the same durations. Sometimes they are long, sometimes they are smaller. Since my, oh, okay, it started working. Okay, so more realistic picture is something like A, B, C, D. Okay, so more realistic would be like this, and this, and this, and this. Okay, like that. Okay, so some of them are short, some of them are longer. Why? Why some of them are, okay, this is time again. Between these two, from here to here, the CPU is on process A, then process B. This is A, this is B, and this is C, and A again, and this is B. Some of them are longer, some of them are shorter. Why? They are not using exactly the same time slices. Yes.
Maybe some instructions take more cycles to finish.
Yes, but I mean, in this part of the CPU time, there might be hundreds or thousands of instructions being executed. So, doesn't matter. I mean, if you wanted to allocate the same amount of time to each of them, then you can do it. But we are not doing it that way. Some of them are shorter, some of them are longer. Why?
Priority?
Maybe, but before that, yes.
As you see here, it's mentioned the picture, one program is active at once. So the one that is not well ticked, it means it's not up, it's active. The process active. Like C, for example.
C, yes.
You see the point on C is different from the other one. I mean the trace.
You mean this one?
No, the active picture.
This one?
Yes.
Yes, so what?
C,
Yeah.
the line of C is different from the other line.
No, it's not different, it's the same. They are all the same. I am not asking about the question here, I am asking a question here. Some of them are longer, some of them are shorter. Why?
Three of
They don't have the same time slice.
You said that? And what? Yes? What did you say?
They have different time slices probably.
No.
three of them could be blocked, so
Yes, this is blocked earlier because it needs some operating system attention. It is doing some kind of an I/O. So it blocks early. This one didn't block. This one blocked early too. This one didn't block. But this one, even though this one didn't block, operating system cuts it. Operating system says that, okay, you ran long enough, okay, I'm gonna block you, I'm gonna let this process run. Okay. So two things might happen. One, the process might get blocked because it needs some kind of an I/O. It will ask the operating system to do something. The other thing is that it runs too long. If it runs too long, then the operating system will stop it. Okay, the operating system will stop it. Okay. So this is kind of Both of them are multi-programming ideas. If you let your programs run to the completion or run until they block, you are doing multi-programming, okay? But if you say that you run too much, you run too long, then you are doing time sharing, okay? Multitasking. Multi-programming and time sharing are very similar, but if you have an interactive system, you have to do the time sharing. You have to do the multitasking. Otherwise, some process might get the CPU, and without asking the operating system anything, it might continue running forever if it is calculating something, an infinite loop. So if you don't block that process for a while, then no other process will get any chance to use CPU. So multi-programming doesn't mean that you can have an interactive system on such a computer. You need to have preemption. Preemption means that stopping a process while it is running to let the other processes run. Okay? You preempt that process, and we will talk about that. Okay? So let's talk a little bit more about how do we create processes and how do we terminate them. There are 4 cases of process creation. Other than the 4th one, the first 3 are very frequent and it is used all the time. First, when the system is initialized, okay, when the system is initialized, the operating system automatically creates processes, and those processes starts running. For example, I showed you the login process. Remember, the login process is created when this computer boots up. Okay. Similar to that login process, there are email servers, web page servers, news servers, and printing servers, and etc. They are all running in the background. Okay. They wait until they have a chance to run, and they are called daemons. Okay. This is a Unix term. Okay, this is a term that comes from the 1960s again. This is a Unix term. So this is the first case where you create a process. The second, the user himself, execution of a process creation system called, the third one, a user requests to create a new process. When I go there and click here, that means that I want to create another process which is called OpenOffice, which is very helpful to create and edit presentation, etc. So this is the second case where you start a process, the user initiation. Okay, it is not always a click case. Sometimes, okay, I use the shell. Okay, I did this. Okay, when I say ls and hit enter, I started a process named ls. Okay, and it ran and it completed its task. Task. So this is the third case for creating a process. Another one is the execution of a process creation system called by a running process. Each process, when they are running, they can create other processes. Okay, so when I do this, okay, there is a process running this bash. Okay, bash created another process, ps. So processes can create other processes. They can create other processes too. So this is the second case, execution of a process creation system called by a running process. Okay. So there is an operating system called, in Unix it is fork. When you call fork, you can create another process. Initial processes created by the processes itself, and the processes created by the user initiation. And there is a fourth process. It is the initiation of a batch job. What is a batch job? We talked about it actually. Batch job is the very large jobs that are very repetitive jobs, like the calculation of the banking account balances for all the banking customers in my bank, etc. If I wanted to do the banking account stuff at the end of the day, There is an automatic process initiation task that initiates the process so that all the accounts get updated for that day. So we don't use this much, but the book has it, so I put it in here. So the most common ones are this is definitely done, okay, this is definitely done, but most of the time it is this one. Okay. Without this one, there is no user interaction. Our system is kind of a batch processing system because there is no user in this case without this one. With the user, I have this one, okay, and with the user, I have this one. I create many processes. I created, when we go back to there, okay. For example, in these processes, okay, I created this one, I created this one, I created this one, and this one. So for five of them are created by myself, and this team member was automatically created when the system booted up. All the rest of them are created by the operating system itself when the system started, or the other processes created them. This is a very important process, this init. Can I see more details? Okay. So this is, okay, this is running, this is coming from this, actually, this bash stuff. Okay, let me come back to this later because I will talk about it in a few minutes. Okay, let's talk more about process creation in more detail. For Unix, to create a new process, there is only one way. It is called fork. Okay, you ask the operating system to create a new process. You make this operating system call fork. Okay, so if I am running Linux, I am running Linux here. When I say ls, the shell takes this command and it forks a new process, okay, and it changes image core image, and lets this program run ls. So it is using fork. Actually, we wrote a simple. Remember, we wrote a simple shell. Very simple shell code for the Unix operating system. If I can find it, we wrote it when we talked about the system calls. Okay, did you see it?
Geçtiniz hocam. Aşağı yine geçti. En alttaki kırmızılının yanında.
Sayısı
57 mi hocam?
60'tan sonra.
60'tan sonra.
63.
Okay, so I read the command. It's like this one. Okay, it is waiting for something to be typed. I say ps and enter. I read the command. Okay, and I fork, run the fork. Fork creates another process which is exactly the same as my process. And I will say that if I am the parent process, I will wait child to end. If I am the child process, I am going to change my core image with the given command, which is ps. So for the Unix environment, I have fork. Okay, usually the child process then executes one of these execution system calls. In this case, I used exec ve with the command line arguments and everything. Okay, so I use that one. When the user types a command, say sort or ls or ps, whatever, this line says whatever we did with the other program. Okay. For Windows API, we don't have fork, but we have create process. Okay. Create process both creates a new process and executes a new command. So it is fork plus execution system call. So both of them comes together. There is no system call named fork for the Windows operating system. Okay. Windows has about 100 other functions for managing and synchronizing the processes. For Unix, we don't have that many. We have a few of them. Okay. So there are very, very specialized versions of it. But for Unix, which was fixed like 2-3 decades ago, 30 years ago maybe, they are using this stuff. So to create a process for Windows and for Unix, we do this. Okay. Usually, when the book talks about an examples, it gives an example on Unix, okay, or Linux, and it gives an example with the Windows. Okay. It doesn't give that much information about Macintosh operating system because the Macintosh operating is kind of closed. They don't document it very well. They don't let people know their internals because they are kind of jealous. They don't. They are against open software. They are against people writing specialized code for their machines. Okay, for the process termination, we talked about process creation. Let's talk about process termination. Processes can normally exit. In Unix, it is you call this system routine exit in Unix. For Windows, it is exit process. Okay, this is a normal exit. There is an error exit. That means that my program cannot open a file, so I have to exit. So it is exiting with an error code. That's the second way. The third one is there is a fatal error. My program cannot continue because I made a very big mistake in my program and I don't know about it. So the operating system kills my process. When I execute an illegal instruction, if I try to reference somebody else's memory, okay, protection, and if I try to divide by 0, okay, so in that case, involuntarily my program will be terminated. These two are voluntary. One is voluntary, there is no problem. Voluntary, but there is a problem. This one, involuntarily process termination. Again, another involuntary, it is killing by another process. I can kill, if I have the permissions, I can kill any process that I want by sending a signal. Okay, in Unix, this code is a kill. This is a kill command. I can send a kill signal to any process that I want. Let's say, let me run a
Find command.
Let me run a command that, okay. So when I say PS, my process ID is -2. If I wanted to kill this bash process, the process of bash, I will say that I'm going to send the signal number 9 to this process number 2. Number 9 is killing the process. See, when I run it, the whole thing gone because I killed my bash. It's not there anymore. I can create it again. So I send that signal to that process and it is gone. The same thing is, again, it exists for the Windows. It's called terminate process. Of course, the killer must have the necessary authorization to do for the killee. Okay, if I want to kill somebody, I have to have enough authorization. I have to have enough authorization. See if I can get PS minus O FX E. Okay, see if I can kill this -9 and 1. -1, -9. No, I cannot kill it because I don't have enough permission. Init is a special process that is created when the system starts, and it starts all the other processes for me. Okay, so init is kind of the root process, and I cannot kill it. But if I try to do this, something happening. I don't know what's happening.
Hocam su dolunca şifre istiyor ya. Normalde.
Su olunca ne?
Su yani yönetici olunca şifre istiyor ya hocam. Şifrenizi bekliyordur belki.
Şifreyi buraya yazmaya çalıştığınız zaman okuyacaksınız ama. Öyle var mı?
Linux'te yazmıyor hocam.
Yok, istedi zaten şifre burada. Böyle bir sakatlık oldu. Belki de ki...
Sen
Ha tamam bir dakika. Suda otomatik, yani ilk defa şifreni daha önce yazdıysan... Yok. Bir daha. Bu orijinal Linux olmadığı için burada saçma olabilir. Başka bir sürü prosesle görmem lazım. Ben hiçbirini görmedim. Okay, so there must be some kind of a way of killing processes. Okay, normal, voluntary, involuntary, and involuntary. There is always a way of creating a process and killing process for all the operating systems. We just saw two examples. Okay, but for the Unix or Windows operating system, I usually do this. I get to the task manager, and I come here and it is end this program, and it is gone. So it is gone. So for Windows, remember this windowing stuff, the graphical user interfaces are part of the operating system for Windows. For Unix, it is not part of the operating system. So most of the system calls for Windows are related to graphical user interface and that kind of stuff. That's why POSIX have much smaller number of system calls than the Windows API. Windows API lets you use graphical interfaces to do some system level calls. For some systems, when a process creates another process, the parent process and child process continue to be associated in certain ways. In Unix, for example, when a process creates another process, the creator is the parent, the other one is the child, and you cannot change it, okay? You cannot change it. If you send a signal to the parent process, that same signal is received by the other processes, the child processes too. Windows has no concept of process hierarchy. There is no child-parent relationship in Windows. They didn't design the operating system that way. That's the design of the operating. But in Unix, there is a very strong child-parent relationship. If you kill the parent, all of your children will be killed. That's the default. That's the default behavior. But for Windows, it is not that way. There is a way of building this process hierarchy in Windows too, but it is not within the kernel of the Windows operating system. All the processes are equal for Windows, but for Unix, there is always a parent-child relationship. There is always a parent-child relationship. Okay, the processes. Okay, when you run a process, it might be in one of the many states, and we are going to look at those states. The book gives this example. Let's say I have this concatenate chapter 1, chapter 2, and chapter 3. I cat them on the screen and grab this word tree from this example. So when I write this line of code, there should be at least two processes, one for the grab, one for the cat, right? Two processes, and they might be running at the same time. The book says that this is an example directly from the book. The book says that depending on the relative speeds of the two processes, it may happen that grep is ready to run. So if I run grep first, okay, maybe grep started running, so it is running, cat has to wait. But for grep to run, it needs some kind of input, and input is going to be produced by this process called cat, okay, catenate. So grep has to wait until cat is producing some kind of an output. So at the beginning, grep is running, this is in blocked state. Now grep goes to the blocked state because the input is not available. Now is cat will get a chance to run. So this one is blocked and this one is running. So that means that there are at least two states. One is blocked, one is running. There is another one actually, ready state. Okay, there is a running state, there is a blocked state, and there is a ready state. And this is a very nice figure from the book again. It talks about these three states of a process, and it talks about how do I go from one state to another state. If I am running, okay, let's say if I am running like this grep. Grep is running and it is looking this word tree, okay? It is looking for this word tree. Since input is not available, then I would go to this blocked state. Why I go to blocked state? Because the data I need is not available. I ask operating system to give me some data. Okay, the operating system looks at the data and it's not available. So operating system blocks my process. Now grep is in the blocked state. Okay, if I am running this command cat, all the data is available. My input is available. So I keep running. So the cat process is running. Grep process is in the blocked state. When my data is available, my process will be brought from blocked state to the ready state. I mean, it is not, I don't go to directly from this state to this state, blocked to running, no. I have to go to ready state. That means that operating system knows that I am ready to run. So when it gets a chance, it will let me use the CPU. But I have to go to ready state. When it gets a chance, I will go from ready state to the running state when the CPU is available. Okay? So this number one is when I am blocked. Number four is when my data is ready. I am in the ready state. And number three is going from ready state to the running state. How about number two? When do I go from running state to ready state? I was already running, then I am going to ready state. What's happening here?
When it has been too long.
Yes, my process might be running too long. Even though I can continue, the operating system says that no, somebody else needs the CPU. You are gonna stop. Okay, so I stop and I go to the ready state. Some other process, there must be some other process in the ready state, so operating system will let the other process run. If it is blocked or if it goes ready state, maybe my process can start running again. Okay, so this is very important, this number two. It is called again preemption for the interactive systems. When we are doing multitasking, I have to use this line. Okay, any questions on this? This is very important. If you understand this figure, you understand most of the operating systems actually. Okay, but the thing is that the information that I gave you until now is not enough to understand this picture completely. Okay, there are very important stuff missing in this picture. When I say that operating system is a process, right? It is just a process. It doesn't have any mechanisms of telling another process to stop running. If the process is running, that process is running, right? Operating system cannot run and stop that other process. So how does this thing is happening here, number two? If a process is running, there is only one CPU. Who is going to stop it? Operating system, right? Operating system is another process. If that process is running, how come the operating system can run and stop the other process? Anladınız mı soruyu? Operating sistemin bir prosesten farkı yok ki. Nasıl running bir proses operating system? Hani bir CPU var elinde, CPU'da bir proses çalışıyor değil mi? Çalışan bir proses operating system kendisini başka bir proses olarak nasıl durdurur ki? CPU'da aynı anda bir tane proses çalışabiliyor değil mi? İkinci bir CPU olsa belki anlayacağım orayı. Orada da gerçi onu yapmıyorlar ama nasıl oluyor bu iş? Şunu anlamak kolay. Buradan buraya nasıl gidersin running'den bu hafta? IO'dan ne? Running şey ne diyor? Operating sisteme diyor ki bana bir tane data lazım diyor. Operating sistemin eline veriyor zaten topu, tamam mı? Topu operating sistemin eline aldığı zaman operating sistem diyor ki tamam, senin bu datan hazır oluncaya kadar seni bloklayacağım ben diyor. Başkasına izin veriyor. Orada bir problem yok. Block birisini ready'ye getirmekte de problem yok. Niye? Çünkü data hazır olduğu zaman bunu bekleyen kim vardı diyor ya. Bu vardı. Öyleyse ben bunu ready yapayım diyor. Ready'den ready'ye getirmekte de problem yok. Değil mi? Bakıyor işletim sistemi. Bunlardan hangileri ready? Bu. İlk önce bunu çalıştıracağım diyor. Hadi çalış diyor. Çalışan birisini kesmek nasıl olacak peki? Nasıl kesiyorsunuz çalışan birisini?
Süre vererek hocam.
Ha?
Çalışma süresi vererek.
Çalışma süresini nasıl kontrol edecek ki operating sistem? Adam çalışıyor.
İnteraktif ya da sinyaller de olabilir mi? Belli bir
Tamam, söyle.
Ondan sonra operating sistem bir kısmını yapar, ondan sonra hemen interrupt ya da sinyal fırlatır.
Timer'lar var. Hardware'den çok yardım alıyor. Şimdi interrupt'lar ne işe yarıyor? Why do we use the interrupts for? If data is ready, if some I/O device produces some kind of an interrupt, an interrupt stops the current process, okay, and lets the interrupt handling routine run so that you can handle that interrupt, right? There is a special interrupt called timer interrupt. Okay, that timer interrupt is set up by the operating system when it starts. Okay, it produces an interrupt every 50 milliseconds. Okay, 20 times a second, maybe 5 milliseconds sometimes, maybe 200 times a second. There is an interrupt happening. Okay, when that interrupt happens, okay, the process is automatically stopped by the hardware, not the operating system. Okay, and there is an interrupt handling routine, and interrupt handling routine is written by the operating system designer and part of the operating system. So a running process is not stopped by the operating system. It is stopped by a interrupt, okay, and hardware interrupt. If you don't have support from the hardware, then there is no multiprogramming with your CPU. At least there is no multiprogramming in terms of time-shared systems, in terms of preemption. You can always go from running to blocked without any help from the hardware, but if you wanted to do number 2, you need help from hardware. Your hardware should provide this timer mechanism. Your timer, okay, you set up your timer, you say that wake me up in 5 milliseconds, for that process may run in 5 milliseconds. Before 5 milliseconds is over, if the process asks the operating system to do something, then it is blocked. That's okay. But if 5 milliseconds over and the process is still running, then there is a timer interrupt. That interrupt happens, and when the interrupt happens, the operating system routine is run automatically, then the operating system comes into the picture and does whatever it wants to do. So again, this doesn't make the operating system any more specific than other processes. It's just a process, but it gets help from the hardware. Since it is the first process to run with the computer, it has to right to set up these timers. Okay, it sets up its timers. It says that only I am going to use these timers. Nobody else can use these timers. So nobody else can do scheduling other than the operating system. These timers were always there from 1970s, 1960s, but everybody had access to those timers, CPU timers. So your process can do some timing stuff. It can do some scheduling and that kind of stuff. So that made the computers very, very unrobust. That can easily crash because you can do your scheduling yourself without asking anything from the operating system. Those were the days of difficult programming times. Okay, any questions? So it's going to take some time to understand this picture filling. Okay, you need to read a lot. You need to do the homeworks, because homeworks is going to try to explain you how you run these 3 states, how you do these transitions. Okay, and you need to think a lot. If you spend a good enough time, and then you will understand it. The danger is that when you look at this picture, it is simple enough. You think that you understand the picture. No, you didn't understand it. Okay, it will take some time. You understand it when you understand it, but if you don't understand it, you don't know you don't understand it. That's the danger. Okay, so I will tell you when you understand it. I understand it from the question that you asked, or from the answer that you give me. Okay, that's it for today. Tomorrow there will be a problem session again. We will take the attendance. Wednesday I will continue with the rest of the chapter.